Well, good morning to my favorite people in the world wanting to learn more of the what they so call say hard stuff, right? Although when you study it, chemistry's not that bad when you really put your brain into it. You see patterns and it's not as bad as people think it is. Just like learning a new language or learning a new musical instrument. It's not easy at first and it can be very frustrating and you feel awkward or it can sound really bad, but the more you do it, the better you get. So treat this the same way, my friends. we're cranking through our chemistry journey, I'll tell you that. It's going to get a little, although it will get a little more challenging today, but two really main concepts I want to get across to you. And, I try to break them down. My brain tends to think about things in a little more simplistic fashion. I love analogies and stories and things like that. Harder to do over videos. I love being interactive with classes much more, but hey, if this helps you, rock and roll. And since apparently I talk fast and go down lots of bunny trails and then come back because my focus issues, hey, whatever, you can just rewind the video and play it over again. The good thing about this is you can pause it and write down what's on the board on your notes. I highly recommend you do that rather than just sitting and watching it. Write this down, write this stuff down, because there's something, I'm not a psychologist, but there's something that happens with the neurons in your brain when you actually physically write it. It's got to go through your brain. It has to process from what you're visually seeing, and something happens in your brain to be able to write it down that causes you to retain more rather than just sitting and watching it. I don't know what it is. Same thing's true when I'm reading a book, right? When I was reading textbooks or whatever, I'm reading a book on how to get through college. I got 4 kids and they're all going to be teenagers at the same time. I'm going to have 4 teenagers in the house in a few years. Hear me, please. But they're all going to be pretty much hitting college, almost all this at the same time, very close. So I'm reading a book on how to get through college debt-free, right? Without having any student loans at all. Oh, there's a lot of information on how to take SATs and ACTs and all this information. And so I'm writing it down. I literally have a clipboard with a piece of paper, and as I read a chapter, as I see something I think is important, some of you are highlighters, but there's something different between highlighting, which is great because if you reread it, it points it out. I do that with some self-help books and things like that. So if I read it a second time, I see it. But if you write it down, I don't know, there's just something that happens in your brain that retains it. Yeah, go ask a psychologist. All right, anyway, down that rabbit trail. We got to look at multi-electron species today because only hydrogen's the only neutral atom with 1 electron. That's what Schrodinger and Bohr, they were working with. Great. What happens if you have 2 electrons? And we even looked at hydrogen-like species, right, that had multiple protons, but they only had 1 electron, so certain types of cations. Great. But what if I want to do like a carbon atom? Simple carbon, or just a simple helium atom with 2 protons and 2 protons and 2 electrons. We have not accounted for the electron-electron interactions yet. Oh no, it's going to get crazy. It messes things up. So we're just going to play around with it to try to get, we know the math works for 1 electron species. So essentially we're just going to take multi-electron species and manipulate them into 1 electron-like species so we can apply the Schrodinger's equation. All right. So let's focus again, kind of review on 1 electron species, what we've learned so far, right? And we did all the shapes with orbitals, but if you look back at that, there was an equation they gave you. This came back with Bohr. The energy of a particular n level, principal energy level, was the negative of the Rydberg constant divided by the principal quantum number squared. And they were quantized. So you had the n equals 1, n equals 2, n equals 3, n equals 4. And then we broke each one down based on their L values. Those are the sublevels, like the 3s, 3p, 3d. And each sublevel is broken down into a number of orbitals based on the m sub L values, the magnetic quantum number. What we get out of the 1 electron species, like hydrogen, is that all the subshells are degenerate. That's the word I want you to remember. Degenerate, not like your little brother degenerate type of thing. You little degenerate. They're the same energy. That's what that means in chemistry. Same energy. So there's only 1 sublevel and 1 orbital in the n equals 1 level, so it doesn't matter. But when you get to n equals 2, you get 2 sublevels, the s and the p. So all the orbitals within a given sublevel are the same energy, degenerate. But all of the sublevels within the given n level are the same. So 2s and 2p, based on this, are the same energy. 3s, 3p, 3d are the same energy. 4s, 4p, 4d, I had trouble getting those 7 orbitals in the 4f. They're all the same energy, okay? It makes life kind of interesting, but that's for 1 electron species. when we get to anything that has 2 or more electrons, we have to account for electron-electron interactions. You're going to see these break apart. The 3s is no longer equal to the 3p, which is no longer equal to the 3d. So one of them is going to be lower energy than the other ones, and there'll be a low, a middle, and a high between the 3s, 3p, 3d. So I want to look at why that happens and the net result of that, because we need to know the energy levels of these sublevels, so when we put electrons into them to do electron configurations later, we know which one it goes into to give us the lowest energy or ground state atom. Atoms want to be in their lowest energy state, called a ground state. Let's look at what happens when we account for electron-electron interactions. So for multi-electron species, there's a couple factors we have to account for that we really didn't for single electron species. And it changes things a little bit. First, if we have multiple electrons, we now have to account, because all we had to account for before was that single electron in the nucleus. Hey, attraction, yay, one's negative, one's positive, easy peasy. But now we've got multiple electrons. So we not only have to account for the electron nucleus attractions, we have to account for the electron-electron repulsive energetics, because they're both negative, aren't they? So they're not going to like being around each other as much necessarily. So we have to look at the fact, and the more electrons you have, the more electron-electron interactions and changes to the energies you have to account for. Right? So we got to look at that. That's going to really complicate the issue. And then we also have to account, if we have more electrons, we're probably going to have more protons as you go along the periodic table. Keeping atoms neutral, you're adding 1 electron for every proton you add, right? So from hydrogen to helium, you're adding 1 electron, 1 proton. You get to carbon, you're up to 6 protons and 6 electrons, right? So as you increase electrons, unless you're dealing with ions, that's a different thing, but you're still increasing the number of protons in the nucleus. So would it make sense that if you increase the number of protons in the nucleus, the overall charge of the nucleus goes up? We call that the nuclear charge, Z. So that's increasing as you add protons. Well, wouldn't you, as an electron negative, be more attracted to a nucleus that had more protons or a higher Z value? Yes. So what happens is it pulls all those electrons and those orbitals closer to the nucleus. And as you know, you get closer to the nucleus, it lowers the energy. So all of the energy is lower. So on that thing I showed you in the last board, all those sublevel energies, all of them would get lower and closer to the nucleus, right? So all of them get pulled closer to the nucleus as the nuclear charge goes up. So all of the orbital energies will decrease. So we have to account for both of these. What we're going to focus is more, and we sort of looked at that where we looked at that, taking into account the Z factor, which was included in some of those Bohr energies. I think it was Z squared or something like that. So sort of looked at already. We haven't even looked at that yet. Let's take a look at it. 2 factors we're going to have to look at when we're looking at how these electron interactions affect the sublevel and orbital energies. Right? So we got to look at 2 things here. What's called electron screening or electron shielding. I've heard both terms, means the same thing, screening or shielding. It's like when I'm doing my sword fighting, right? Some people, I like to fight with 2 swords. Some people like to fight 1 sword shield, because that shield blocks my sword from hitting them. Oh, it screens their body from my sword. So I really always hated fighting people with shields, right? Because it'd be so irritating. I like to just like a weed whacker, because my speed, I was really fast. And what happened was somebody had a shield that slowed me down, really bothered me. So I had to slow down and think, how do I get around the shield? Especially I was a little guy, so you get some 6'3" dude with a big tower shield. I'm like, how do I get around that? Broke a lot of swords on those shields. Anyway, let's get off of that bunny trail. So I'll talk about that in the next board. And then we'll look at each one separately, even though they overlap a lot, but I'll try to treat them separately. And the other one is orbital penetration as well. We'll look at, based on the fact that the sublevels have different shapes, right? That's what the L value is. The angular momentum quantum number looks at the shape, right? So we know S orbitals are spheres, P orbitals have those 2 lobes, D orbitals have the 4 lobes, except for the DZ squared, which is a P orbital with a hula hoop around it or a donut. And then the F orbitals were the 8 lobes. At least 4 of them were, and then 3 of them were the p orbital with the 2 hula hoops around it. Wooga, wooga, wooga. Well, those different shapes really have different electron densities around the nucleus. So yeah, that might change some energies there, or how electrons prefer to go into different orbitals, right? So let's look at electron screening or shielding first. I think that's easier to think about qualitatively. Orbital penetration is a little bit tougher, so we'll put up some plots and stuff so you can look at it, and hopefully that will help a little bit. All right, gang, let's look at electron shielding or electron screening. So I kind of wrote, essay format what it is, and then drew a picture of it. I think pictures work easier. It's kind of like me when you go to a movie or something. When the movie's open back up, a lot of times I like to go early and watch previews and all that fun stuff, and I'll find a nice seat. And it's just uncanny how it works out. And I like to go on weekdays, right? I don't like people sitting in front of me because I'm height challenged, so I don't like my view impeded by someone else, right? And invariably, there'll be times when there might be 10 people in the entire movie theater. I'll be sitting there, previews are over, movie's about now. I got my legs kicked out. I'm like, yeah, feeling good. And some 6'3" dude comes in and sits right in front of me. I'm like, kidding me, there's got to be like 400 seats open, and this hose head just sat right in front of me. I'm like, are you kidding me? Have you ever had that happen to you? Right? And you're like, oh, right? Or you're at some concert or something. It's like, oh, come on, take the hat off. Drives me nuts, right? It's like, oh, so I'll get up and move over here, and then somebody else is done. It's uncanny. Well, imagine you're an electron trying to see you're negative and the nucleus is positive. Ooh, I like the nucleus. It's nice. So electrons in that n=1 energy level have an unimpeded view of the nucleus. So they see the full effective nuclear charge, Z. They would see Z, right? But as you move, remember, there's only so much space, right? When that's full, the electrons go into higher energy or further out energy levels and orbitals within those. So you get, n=2 fills up. So let's say we're an electron way out in n=3, right? And the nucleus would be like the screen for the movie theater. And that's me in purple sitting there. And I'm trying to see the screen, and all these tall people are sitting in front of me, and I'm like, hey, hey, hey. Or if you're trying to see that nucleus, and all of a sudden I go, hey, can you see it? Can you see it? Can you see it? Right? You get so irritated. So would you agree that outer electron does not see the full effective positive nuclear charge of that nucleus because these other electrons screen it away. They shield it. Whoo! Right? I can't hit you with my sword. So we can't use the full value of the nuclear charge if we're talking about an electron that has other electrons between it and the nucleus. Oh, and we got all these electron-electron interactions. What do we do? Right? So electrons residing in lower energy or inner shells block, or partially block, they don't completely block, partially block the nucleus from higher n level or outer electrons in those shells. So that reduced nuclear charge we call the effective nuclear charge, Z sub EFF. Right? So if carbon had a Z value of 6, its outer ones wouldn't see a value of 6 protons. They'd see a reduced one. So whatever, we're not going to have to calculate that in this class. It's a little more complicated. So let's say it was a 5.2 instead of a 6. You'd have to use that value from Z in your wave mechanical calculations, like the Schrodinger's equation. You see that? So the shielding forces us to use what's called an effective nuclear charge. And ultimately what we're going to do is we're going to reduce multi-electron species into one electron species. And what we're going to do is we're going to take all these inner electrons and the full nucleus, combine them, and leave just a single electron for and with a reduced nuclear charge, and then we can do the wave mechanics on a one electron species. So this is ultimately what we're going to do. I took so much time to draw this, I hate erasing it. So what we're going to do now is we're going to do this. Right? So normally that would just be Z, right, for an inner electron. But what we're going to do is take all those other electrons, pretend they go bye-bye, right? And now what you get is an undisturbed look at the effective nuclear charge, but we reduce the nuclear charge, so we collapse this into a one electron situation, right? So what we're going to do is we're going to collapse multi-electron species into one electron species, right? So we're going to take that multi. So all those others, it doesn't matter if there's 5 electrons in between that electron and the nucleus or 50 or 100, doesn't matter. We're just going to take all those electrons, take all those energetic interactions, and create a 1 electron scenario with a reduced or effective nuclear charge. So collapse the multi-electron species into 1 electron species. With Z effective, right? So that's how we're going to apply Schrodinger's equations. And so we're going to get what are called hydrogen-like orbitals. So they look the same, right? It's the angular distribution is still exactly the same. It's just the radial distribution changes. They all get pulled closer to the nucleus. And we're going to find out that some orbitals, like SPDF, some of them shield better than other ones. And that's what we have to look at with orbital penetration next, is based on the electron probability, is it closer to the nucleus versus not, right? Some of them shield outer ones better than others, and so what happens is the SPD and F sublevel energies start shifting around. All of them get pulled closer to the nucleus because we have increased nuclear charge, right? So this is pretty important. So this creates what are called hydrogen-like orbitals. They look like hydrogen orbitals, right? The P's look like P's, D's look like D's, but they all get lowered in energy, and then the sublevels start to shift. So I'll summarize that on the next board. All right, here's the net result of electron screening, and it's going to overlap with orbital penetration next, so hopefully you'll see that. But all the new hydrogen-like orbitals, they look like the hydrogen orbitals, right? Because the angular functions are the same. Just they all get pulled closer to the nucleus as you add more protons. Adding more electrons, you add more protons. So the Z effective is increasing. All of the orbitals get pulled closer to the nucleus, which means they all lower in energy. So if you've got hydrogen, I'll show them this next to each other. Hydrogen orbitals might be here. Hydrogen-like orbitals will be lower in energy because they're getting pulled. More protons, right? Pulls the electrons closer, right? Also, and this is the key, the sublevel energies lose their degeneracy. Remember, for a hydrogen, 2s equaled 2p, 3s equaled 3p equal 3d, 4s equaled 4p equals 4d equals 4. They're all the same energies because of the equation. But when you account for electron interactions and electron screening, they have different shapes, right? S is spherical, P is the 2 lobes, etc. They have different electron densities near the nucleus, so they will screen other outer electrons differently because of the different shapes. We're going to look at orbital penetration next so you can see it a little better, and I'll give you the result when we're all done talking about it. But what happens is the degeneracy of the sublevels breaks down, which means the 4s does not equal the 4p anymore, which does not equal the 4d, which does not equal the 4f. They are no longer degenerate. They shift in energies, which means some will become more preferable to fill than others because electrons want to, go in the ones with the lowest energies because the atom wants the lowest energy state. Ooh, we'll see the result after we look at the shapes of these babies. Let's do orbital penetration next. All right, hopefully this makes common sense to you. We know based on the angular momentum quantum number L, you get different shapes, different angular electron distributions or electron probabilities, right? So we know S, which is spherical. P has the 2 lobes with a node right there, where there's no electron density at the nucleus, whereas the s orbital, they're by the nucleus, right? So can you see how an s orbital, because it has more electron density close to the nucleus, will screen outer orbitals more efficiently than P, which has a 0 electron density or probability at the nucleus. Same with D, with the 4 lobes, it has 0. Even the p orbital with the hula hoop, there's it's just not as much as an s orbital. And f orbitals also have a 0 at the center, right? So s orbitals by far have more electron density closer to the nucleus. Because of that, right, that there's more electron probability near the nucleus, that means it's a more efficient screener. So some shapes have more, because they have more electron density or probability close to the nucleus, they shield outer ones better. That's called orbital penetration. I'm going to show you this graphically, okay, on the next screen. I'll show you like 1s versus 2s versus 2p versus 3s or something like that, and show you that the electron probability about the nucleus is greater for some than others, which means they're closer to the nucleus. They penetrate closer to the nucleus, and they screen outer electrons more effectively, and they're more likely to fill first, right? So if an electron's going, hey, I want to get as close to the nucleus as I can, it's like going to a concert or something like that. It's like, and it's open seating. Like if I go to a Sick Puppies or concert or something, I'm like, I want to get there early and get into the mosh pit and get as close to the stage as possible and watch the bass guitarist go, 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 right? Maybe I'll throw a pick at me or something. Well, that's the same with an electron. They want to, even though it kind of has, they can't all go in the n=1, but there's limited amount of electrons that can go there. They want to get as close as they possibly can. So orbitals that have a better view of the nucleus will tend to fill first, right? And they screen the other ones better. All right, so that's going to cause the degeneracy to break down. So let's look at some of these plots so you can actually see it. All right, this is a little weird to think about. We're going to look at electron probability or electron charge density distribution a little bit differently than we did when we looked at orbitals. So what we want to do is we're going to look at what's called a radial probability distribution plot. So in essence, here's the nucleus, and then the radius goes further and further from the nucleus, right? So instead of looking at just that point, what we want to do is go a certain distance from the nucleus and look at the entire sphere around it. Try to get like this infinitesimally thin sphere surround, like an onion's, a layer of an onion or a banana peel or something like that, you know what I mean? Around it, that'd be a weird looking banana peel, but you get that, or let's say an orange peel, right? And we look at, what's the electron density in that sphere, that thin sphere around the nucleus, and as you get further and further away. So we want to look at, as we get further from the nucleus, how does the chance or the probability of an electron, the electron density be as you get further away in that sphere, all right? So R squared, that's the radial probability density, just moving from here to here. If you multiply that, right, by the volume of that sphere, then you're looking at that whole region around the nucleus. So we're going to take the volume of the sphere, right, which would technically be an area because it's infinitesimally thin, 4 pi r squared or something like that, I forget what it is. Multiply those together and you get the radial probability distribution. And I'm going to draw some graphs on that. And I think it really gives you a bird's eye view of where electron density is around the nucleus at a particular distance from the nucleus, okay? So if we plot that, it gives us a view of what orbital penetration is. I think it's the best view of it. One way to look at it, I do archery, sword fight, anything. Like I'm starting to do guns, but they scare me a little bit. It's really hard to shoot yourself with an arrow, right? I almost did. Don't shoot arrows straight up. Really, really stupid. But if I'm shooting this way, it's really hard to hit yourself, I've noticed. So if you look at, say you're a fairly, you're not a pro or something, and I'm shooting archery at a target, right? I'm going to get I'm aiming at the bullseye, right? So I'm going to get quite a few here, and, I'll miss here, and, I might get 5 points for that, 3 points for that, 1 point, and then nothing here every once in a while. Crud, a string hits my forearm or something, or I haven't done it, because I got bad shoulders, I'll be like this, I'm like, oh, my shoulder hurts on me, and the arrow goes flying. So you get this distribution of arrows that strike. Each red dot represents where that arrow hit, right? You can see that it sure looks like there's a big density of arrows that hit in the center, but that's a small volume. Do you see that? Whereas over here, right, it looks like it's more spread out as you get further away, but that's because there's more volume. So right, it's like having 5 people in a small room versus 5 people or 10 people in a huge room. You know what I'm saying? So if you put 10 people in a huge room, there's more people, but they're more spread out. But fewer people in a smaller room, they look like they're packed in more tightly because they are. So as you look out, there's actually more arrow hits here, but it doesn't really look like it. So what we're doing is we're looking at the combination of the density there and the volume effect. Okay, so that'll really give us a look at where the electron density is as we move in this infinitesimally small sphere or thin sphere further from the nucleus and plot it versus R. This will make more sense when you see the graphs. All right, let's do kind of the 1 and 2 energy levels. Then we'll do 3 to show you it gets a little more complicated. But here's that probability, right? 0%. I went up to about 50% of the probability of the electron density being near the nucleus, 0 being at the nucleus. And let's just take the x-axis as the radius. We're increasing the radius, scaled by the Bohr radius, 53 picometers, right? So we don't do the actual radius. So I'm not doing the specific, we're at 152 picometers away, which you could do. And we'll go up to about 15, even though it tails off before that. So if we do the 1s and plot that radial probability distribution, boom! Most of the electron density is that's that Bohr radius, right? 1a naught at 53 picometers. So the majority of the electron density probability distribution is right in front of that nucleus. Great screener, right? It screens, 1s screens everything out. It's great. If we do the 2s, though, remember we get a radial node. So the 2s, there's a little bit of electron density here, and then it goes to 0 when the radius is 2 times the Bohr radius, so 2 times 53 or 106 picometers, and you get that node. And that, if you remember, if you look back at orbital shapes, it's from that factor that's in the radial distribution wave function, 2 minus r over a naught. So when r is 2a naught, 2 minus 2 is 0, and it goes to 0, right? And then it changes sign. And then boom, you get this huge, so the majority of the electron density for a 2s orbital is out here further than the 1s, and then it tails off, right? We can draw that 95% containment curve. But do you see that little blue dip there? That's called orbital penetration, right? It's like, so that actually screens out a little bit of the other ones. Not as well as the 1s though. Now the 2p, that goes up and then down, so the 2p's in green, and it's pretty similar to the 2s, but the 2p does not have that little bump there, so the 2s actually screens out the 2p more efficiently than 2p screening out the 2s. See that little bump there? I think hopefully you can visualize the penetration there. Let's do it for the 3s, and you can see the penetration a little bit better. This one's a little bit more messy, but here's the 3s, 3p, and 3ds. Let's take a look at the 3s. We got two radial nodes in red. So you get this little dink, and then you get a radial node at 1.9 times the Bohr radius, and then bloop, another radial node at 7.1, so I calculated those, and then boom. So most of it's further out, right, than 1s and 2s. But here's that term in the radial distribution for 3s. We didn't look at this before. So you actually get 2 because of it's a little more complicated. So I plugged in values of r in order to see what radius gave us the nodes and put them in there. You don't need to know that. So you get this dink, dink, dink. Now blue is 3p, right? So we have one radial node. So it goes up and then boop, a radial node at 6 times the Bohr radius due to this factor in the radial function, 4 minus 2r over 3 naught. So when r is 6 times a naught, you get 0. And then boom, the majority of the 3p's over there. But notice that little tiny red hump, that right there. That orbital penetration, that 3s, that little sneaker stuck his head closer to the stage and has a better view. So the 3s actually screens the 3p a little bit more effectively, right? And is more likely to fill. And then when you look at the 3D in green, there is no radial node at 3D. It goes, and then down it goes. And it's way further out. So S screens the P, but the P screens, see this orbital penetration, that first blue hump is way before the green hump. So the 3P really, it screens out the 3D, but not as well as the 3S. Do you see a trend here? S better than P, better than D? Let's summarize it. And then that node there, this factor is in the radial function for the P orbital. The 3p orbital, 4 minus 2r over 3a naught. You can just plug in the numbers to get it. So let's summarize orbital penetration and screening and look at the effect on the sublevel degeneracies. We'll be done. All right, all of that gobbledygook we just looked at, here's the net result of looking at orbital penetration and electron shielding from the electron-electron interactions and stuff. The S sublevel is the best at screening out anyone else, right? And then P, then D, then F. So best screener, worst screener, based on those radial probability electron distributions, right? And you saw those plots with the little peekaboo orbital penetrations. S has the most orbital penetration, electron density closest to the nucleus. more than P, which has more than D, which has more than F. All right? And you can see that in the plots, which means S will have the lowest energy, then P, then D, then F, which has the highest. So for hydrogen, they're all the same. But when you account for multi-electrons, S drops down here, then P, then D, then F. Let's look at that. All right, let's compare and contrast what we started with what we're ending with. So remember, we were looking at the hydrogen atom, where you could look at all the sublevels have the same energy. They're degenerate because we only have one electron. We don't have to worry about orbital penetration and electron screening, right? So 1s, 2s, 2p, 3s, 3p, 3d. That's as much as I could fit on this board. Now let's look at multi-electron species. So I just picked a couple of elements. I picked beryllium and calcium just to show you the effect. Now remember two things. More protons in the nucleus pulls everything closer to the nucleus. So first thing I want you to notice is they all shift lower. As you get, so I go from 1 proton to 4 protons, shifts everything lower, to 20 protons, shifts, actually would probably shift lower than that. I just don't have the space on my board. So let's notice that 1s drops, the 2s drops, the 2p keeps dropping, pulling them closer to the nucleus, lower energies. But now, look at the breakdown of the degeneracy as I get that cat hair out of my mouth. The breakdown of the degeneracies of the SP, D, and F sublevels because of S screening more than P, than D, than F, and S having more orbital penetration than P, than D, and F. Now look at the 2S, 2P. So there's not that many. There's only 4 electrons here. But the 2S drops a little lower than the 2P. The 3s is a little lower than the 3p, which is a little lower than the 3d. Oh, so electrons would rather go in 2s than 2p. They would rather go in 3s, and then when that's full 3p, then 3d. See the filling process? They want the closest seats to the stage. Here's the stage down here at the nucleus. Now, when you get to a lot of protons, the 1s drops even more. The 2s drops even more, and then you get the degeneracy breakdown. The 2p is a little higher. And then the 3s, 3p, 3d. But look what happens here. Remember, as you get further and further from the nucleus, this might be from N1 to N2 to N3 to N4 to N5. They get closer and closer because the 1 over N squared deal. So as you get further from the nucleus, the energy levels get closer and closer and closer and closer and closer to the point where orbital penetration and screening causes this mixing process where the 4s has so much orbital penetration versus the 3d, and the energy levels, the principal energy levels 3 and 4 are close enough, the 4s actually dips below the 3d. So even though it's a higher N level, 4 is higher than 3 because of orbital penetration, electron screening, the 4s has that peekaboo factor, fills first. That will fill before the 3d because it's got a better view of the nucleus of the stage, right? It's like being behind 2 people but sticking your head under their armpits. It's like, oh, I can see better now, right? Even though most of the probabilities, behind, you poke your head up in front, that's that little hump you saw. That's a huge effect, and that's going to affect where the electrons go when we do electron configurations in the next video.